In this video, we're going to review some of the main topics that we discussed in Chapter 1 of the algebra textbook. So Chapter 1 was all about equations and inequalities. We learned how to solve different kinds of equations and inequalities. And what we saw was that the type of equation or inequality that we were dealing with was directly related to the types of terms or expressions that were contained within the equation or inequality. So if it was all polynomial terms, then we were dealing with a polynomial equation. Or if they were all just linear polynomial terms, then we called it a linear equation, or maybe a quadratic equation. If there was at least one radical term in the equation, then we call that a radical equation, or that would be equivalently a term with a rational exponent. Okay, now the vast majority of the equations and inequalities that we worked with contained one variable. So like linear equations in one variable, quadratic equations in one variable, or inequalities, etc. But we did briefly at some points look at equations that contained more than one variable, equations or inequalities that contained more than one variable. These were called literal equations or inequalities. And what we saw was that once you learn the mechanics of how to solve any of these types of equations and inequalities in one variable, then the mechanics when it comes to solving an equation or inequality with multiple variables is exactly the same in every way. So like, for example, if I have a linear equation in 3 variables and I want to solve for x, well, it's not like I'm entering into some new, I have to take a new class on solving linear equations in multiple variables. Add 5y to both sides. Now divide both sides by 3. And there you go. I just solved a linear equation in 3 variables. You see what I mean by the mechanics are no different? However, but yes, it is in terms of analyzing what exactly the solutions mean and just analyzing the whole overarching meaning of these equations in multiple variables. That's going to take a little more. That can be a little more difficult and take some practice to learn how to analyze the equation or inequality. But the mechanics of manipulating it and solving it for different variables are no different than what we learned in this entire chapter, as you can see here. I mean, I could show you a quick example. Let's say we had a quadratic equation in 3 variables. So 4x squared minus 3xy plus z squared is equal to 7xz plus 2y. Okay, we know this is quadratic because every single variable is raised, it's polynomial, every single variable is raised to a whole number exponent, so like positive integer or 0. But then we analyze each term and we look at the total degree of each term, and whatever the highest degree term is, that's the type of polynomial equation it's going to be. And the highest degree term, so this is degree 2, this is degree 2, 1 plus 1, this is degree 2, this is degree 2, this is degree 1. So this is a quadratic equation in x, y, and z. So now if we wanted to, let's say we want to solve this for x. Well, as far as the mechanics of manipulating the equation to solve for x, you treat the other variables that you're not solving for like they're constants, at least as far as the mechanics go of manipulating the equation. So in that case, then, we know that if we're going to solve a quadratic equation, we want to bring everything to one side with the other side equal to 0. So let's do that. Okay, but let's also group, let's group the x squared terms and the x terms and the terms with no x together. So we only have one x squared term. Okay, so now let's group the x terms, so 3xy, let's subtract 7xz from both sides. Okay, now let's group the terms that don't have, subtracting 2y from both sides, and there we go. Okay, so now since we're kind of looking at variables y and z like they're constants, let's factor out an x here and an x squared here where we only have one x squared term, so we don't need to factor anything. But yeah, so let's do this. Let's say we've got 4x squared And let's leave a minus out, and we've got 3y plus 7z, okay, and then x, and then plus, and then we've got z squared minus 2y. Okay, now with this, we can see the general form here. Ax squared plus by plus c is equal to 0. So we can see that a is equal to 4, b is equal to minus 3y minus 7z, and c is equal to z squared minus 2y. We could apply the quadratic formula. Now, what we're going to end up with is we're going to have a square, a principal square root with b squared minus 4ac under it. And so then we'd have to analyze, okay, well, what values of y and z would make that expression negative, and that's not going to be a solution unless we're allowing for imaginary solutions. But you can see, you could go through the whole, as far as yes, this is obviously going to take some effort to analyze this really carefully, because it's cumbersome because you've got all these variables all over the place, obviously. But I'm saying the mechanics are no different as far as solving the equation and solving for different variables, manipulating the equation. Okay, so now, but we started this section with an introduction to equations. So to do this, we learned how to solve two of the simplest types of equations, the linear equation and the rational equation. And what we learned was that an equation or an inequality, all it is that, so you have an equation to where you have this equals sign, and then on one side is some expression of one or more variables, and same on the other side. You have an expression on either side, or it's the same idea with an inequality. You've got one of these four types of inequalities: greater than, less than, greater than, equal to, less than, equal to, and an expression on one side and an expression on the other side. And a solution to an equation or inequality is, so if it's in one variable, then you're picking any number off of the real number line or in the complex plane, and you're taking that number and you're plugging it in to both sides of the equation or inequality. Then you're simplifying and getting a number on either side. When it comes to an equation, if those numbers are the same, then that's a solution. When it comes to an inequality, if the inequality is like, if this number is greater than the number on the right, then it's a solution. It depends on the inequality you have. And you can think about, when it comes to complex numbers, it makes sense we can think about doing this with equations, right? You could plug any complex number into either side and simplify it and see if the left side is equal to the right side. But we can't really think about doing this at the moment with inequalities, because how is one complex number in the complex plane going to be greater than another complex number? How do we define that? So we can't really think about inequalities at the moment with complex numbers. Okay, but again, when it comes to an equation or inequality, we're just trying to find the solutions. We're trying to find one or more numbers on the real number line or in the entire complex plane that when you plug them into one side, you simplify, you get a number. You plug them into the other side, that's that same number, into the other side, you simplify and you get a number that it satisfies the equation or the inequality. There could be one or multiple solutions. Now, if you've got multiple variables, if you've got a multivariable equation or inequality, then, like, let's say you have an equation in x and y, then you're looking for the xy pairs. If you take an xy pair and you plug that into the left side and you simplify, and you plug that into the right side and you simplify, do you get the same number? Then that xy pair, like 1 minus 2, that's a solution to the equation or the inequality. Or if you've got an equation or inequality in 3 variables, then you're looking for all of the triplets that satisfy that equation or that inequality. Okay, and so we started off with the most simple type of equation, the linear equation in one variable, which is it's going to have all linear terms. Every term is going to be a linear term on either side of the equation. So raised to the power 1 or raised to the power 0. In that case, you have a constant, like it's a 5x to the 1. that's linear, but 3x to the 0, that's also linear. It's just a constant. Okay, and what we learned was that when learning how to solve linear equations in one variable, we were introduced to the properties of equality, but these properties of equality didn't apply just to linear equations. These apply to any kind of equation in any number of variables. The properties of equality are the fundamental tools we use to solve any kind of equation in any number of variables. And the whole idea was that if you add the same number, which that could be an actual number or a variable expression that's a placeholder for a number, if you add or subtract the same number to both sides of an equation, then you don't change the equation. You have an equivalent equation, which just means that the solution sets are the same. Similarly, if you multiply or divide the same thing on both sides of an equation, you don't change the equation. Except if you multiply both sides by 0, then you don't have an equivalent equation. If I took x is equal to 3 and multiply both sides by 0, I don't have an equivalent equation. I've changed the equation. And then you obviously can't divide both sides by 0 because you can't divide by 0. Okay, and so the whole idea is we want to use these properties of equality to condense down the equation from a complicated expression on one side and a complicated expression on the other side, all the way down to an equivalent equation where we can just read off what the solution or the solutions are, because it's obvious what the solutions to this equation are. What are all the numbers in the entire complex plane that when you plug them into both sides, this equation is satisfied? Well, there's just one number, it's 3. Plug in 3 to the right side, you get 3. Plug in 3 to the left side, you get 3. That's the solution. And so if this equation is equivalent to some original equation that we're trying to solve, well, then the fact that it's an equivalent equation means the solution sets are the same. So now we have the solutions to the original equation. Okay, now we then learned that there are 3 different types of equations. Any equation, and no matter what kind of equation and however many number of variables, it's going to be one of 3 types. It's going to be either conditional, it's going to be a contradiction, or it's going to be an identity. It's going to be one of those 3. Again, any type of equation, not just linear, no matter in any number of variables. A conditional equation is that, so for all of these types, for all 3 of these types, we want to start by looking at what are all of the possible solutions. So in the broadest sense, this would be any number in the entire complex plane. This includes real numbers, the horizontal axis, but we could be looking at an equation that we're only considering real numbers as potential solutions. But you first, to identify what type of equation you have, you look at what are all of the potential solutions to this equation. Is it going to be all real numbers, or is it going to be all complex numbers? Whatever. If the resulting values that satisfy that equation are only a portion of the possible values, then that's called conditional. It might be like this entire left half of the entire complex plane, but not the right half. That's conditional. Or maybe it's just one complex number or one real number, whatever. That's conditional. Okay? If not one of all of the potential solutions are a solution, then that's called a contradiction. There's no solution. If every single possible solution is a solution, then that's called an identity. Okay, we then looked at rational equations. In this introduction to equations section, we also looked at rational equations because the rational equation gave us another perspective of how we're going to have to approach solving equations in general that we didn't get with the linear equation. Because with a rational equation, which would be any equation that to where at least one of the expressions is rational in the sense of how we defined it informally in pre-algebra, that there's at least one variable in a denominator somewhere that's raised to a whole number power other than 0, or it'd be a constant. If there's at least one variable somewhere in the equation that's in a denominator of a fraction raised to some positive integer power, we call that a rational equation. Assuming all the other terms are polynomial. Like if you have other terms that are maybe radical, then we're going to call that a radical equation. If you've got other terms that are logarithmic, we'll call that logarithmic. But assuming there's no radicals or logarithms, then if there's a variable in a denominator raised, at least just one, raised to a positive integer power, we call that rational. And so the general process to solve a rational equation is we want to multiply the entire equation by the least common denominator. So if we had 1 over x plus 5 is equal to 2, this is rational. Okay, we want to clear the fractions. And so we multiply by the least common denominator. In this case, that would be x. Well, when we do this, we're going to be multiplying both sides of an equation by an expression of x, which means that there's going to be some x values. So let me do this. There's going to be some x values that make that expression we're multiplying by equal 0, right? In this case, if x happened to be equal to 2, then we're multiplying both sides by 0. And so we have to, when we do something like this, we're going to have to keep in mind that, okay, when we get to the end, so if we solve this, we'd get x minus 2 plus 5 times x minus 2 is equal to 2x times x minus 2. We have to solve a quadratic, and we're going to get some answers. We have to check to see if any of those answers are what's called extraneous, which means that extraneous solutions means that we didn't make any math errors when solving the equation, and we got some answers, but those answers aren't actually solutions to the original equation. We need to plug those back in to the original equation to make sure that what's going to happen is, in the case of rational equations, it would be the case that would be one of the values that we multiplied both sides by that would have been 0, which would correspond to, if we plug them back into the original equation, that would be a dividing by 0 case. So that's not going to be a solution. Because if I solved and I got x is equal to 2 or x is equal to 3, well, remember, for any of these to be solutions, remember the fundamental meaning of a solution to an equation or an inequality. You plug it into both sides, you simplify both sides, get a number, you get the same number on both sides. Okay, I can plug 2 in over here, I get 4. If I plug 2 in over here, I get 1 divided by 0. I can't do anything with that. That's not a solution, okay? And now, but you might be scratching your head and thinking, well, where do these extraneous solutions come from? How does this happen? It's just because you have to think about the resulting equation that you get here has no idea where it came from. Like, you multiply both sides by x minus 2, but you just got some quadratic. It depends on, it's just going to, the resulting equation you get depends on whatever you arbitrarily have in these numerators after you clear the fractions. I mean, the stuff in the numerators has no clue where it came from. So it might be the case that you just solve this random quadratic here that you get, or whatever results, and you're going to get some numbers that just happen to be when you go back to the original equation, you're dividing by 0. It's like the same idea when we simplified rational expressions. So if I simplified a rational expression, so I factored the numerator and denominator and got this, and I wanted to simplify. So I cancel those out. I get this. Okay, well, am I allowed to plug minus 2 in here? Minus 2 minus 2 is 4. Well, no, because you can't divide by 0. It's not, the math isn't broken. It's just that this x minus 2 doesn't know where it came from. I mean, it's just a result of the circumstance. You see? Okay. We then looked at different applications of linear and rational equations, and it's important to get a feel for the different types of applications where different types of equations come up. All right. Then in the third section, we looked at we were introduced to complex numbers. We were introduced for the first time officially in the textbook to complex numbers, even though I've brought these up at the beginning of this entire course. So it's not the first time, at least on going through this playlist, you've heard of complex numbers. But what we saw was that where complex numbers came from, so why these new numbers were invented, was because of the need to solve an equation like this. It's because of the need to solve any kind of equation where you have to you need to answer a question: what number, when you take it to an even power, do you get a negative number? Before imaginary or complex numbers, there was no solution to that. There was no real number that when you took it to an even power, you got a negative number. And that's the whole reason these new numbers were invented. And the heart of it is the invention of this imaginary number I. And you treat this like any other number. This is as much of a number as pi is a number. Okay, it's like any other number. But what is this number? This is a number that the meaning of it is that when you square it, you get -1. That is it. Another way of looking at that is that the principal square root of -1 is I. Now, we know principal root means you return the positive root. So yes, I squared is -1, but also minus I squared is equal to -1 because I is a number. So you can apply the properties of exponents. -1 squared is 1. And then we have I squared is -1. That's the meaning of I. However, in order to, this is just defining I this way is not enough to be able to solve any kind of situation that requires you to ask, okay, what number to the 6th power am I going to get -30? What number or numbers when I take it to the 12th power, whatever, am I going to get negative whatever? We need to extend this a bit more to complex numbers, which means that, okay, yeah, we have I, that's fine, and we know what I means, but we're gonna define this entire. Previously, we could graphically think about how we could pick any number off of a line called the real number line. We could pick any number off this line. Well, we need to now extend this to think about how we can pick any number off of this entire plane now. Not just a line, but an entire plane. The original real number line is still within this plane, but now we can move off of that real number line anywhere in this complex plane. And this is the imaginary axis. This is the real axis. And it's two-dimensional because the idea of something being two-dimensional means that you can only you can think about how we're only going to be able to simplify any complex numbers down to 2 parameters. So if we had real numbers are contained on a line because you could always take real numbers and condense them down to a single value, right? If we had 2 minus 3, well, we can combine these to -1, where we'll always be able to condense any real numbers down to a single number that you can put on a line, right? You could for single numbers that's one-dimensional, you can put it on a line. Well, when it comes to the idea of a complex number is you're taking a real number with a real part, and then you're adding to it this imaginary part. So like 3, 1, 2, 3, and then you go up 2. That's 3 plus 2i. We can't simplify this anymore. We can't combine these. They're 2 separate dimensions. There's an I term and there's a non-I term, but we can't combine them. So like a complex number is going to, in general, a real number is going to be just some figure A. A complex number is going to be an A plus BI, where A and B are these real numbers, but now you can pick any point on this plane. That's a complex number. And with complex numbers like this, now we can think about using a complex number, some A plus BI in the entire complex plane. Now we can answer any question we want that involves taking some number in the entire complex plane, and that could be a pure real number, to an even power and getting a negative number, whatever. Now there's no issues with that whatsoever. Okay, now, but what's very important about complex numbers is that the only way they could be invented was that they needed to be able to behave and have all the fundamental properties of numbers, of the real numbers, and they do. If you multiply any complex number by 0, you get 0. If you divide it by itself, you get 1. If you add it to its opposite, you get 0. They obey the property, the distributive property, the associative property, the commutative property, everything. They're numbers. That's why, look, in the complex plane, there's all the real numbers. These are all numbers. How could complex numbers not behave like numbers in every way? How could that not be the case? But at the same time, in the complex plane, you've got all the real number. You've got the entire real number axis in the complex plane. That couldn't be possible. So that's really important to remember that complex numbers, imaginary numbers, behave like numbers just like real numbers. There's only certain caveats can come up that you need to be aware of that we're going to learn, and that we got a sense of a little bit of this in this section, and we're going to learn more about this in trigonometry and complex analysis. The only caveats come up as from a mechanics standpoint, in the sense that we learn how to add, subtract, and multiply complex numbers, and we saw that the mechanics were exactly the same as for real numbers. Okay. But when it came to dividing, it wasn't, it was different in the sense that not that they didn't behave like numbers, but okay, if we're dividing 8 by 2 real numbers, well, we know, okay, that's 4. Well, okay, if we're dividing 8 minus 3i by 4 plus I, well, because of the fact that that a complex number has like this two-dimensional form, well, now we can't divide it in the same way, because division, like I couldn't separate this into 8 divided by 4 plus I minus 3i divided by 4 plus I. We have to go a different route than what we did with just real numbers. But we saw it's just, okay, we multiply by we're still using the properties of numbers to figure this out, because we multiply what we call a complex conjugate by two complex conjugates, we get a real number, and we could turn this into a new complex number. Okay, now, so what we also talked about was that everything that we're doing in algebra with equations, all the equations we're solving, everything we're doing can absolutely extend to complex numbers. And that makes sense, because look, the complex numbers they couldn't be any more intimately related to the imaginary numbers, right? Like these are all in the complex plane. So everything we're doing in algebra is going to extend, no problem, to complex numbers. But we can't do that all at once. We can only take it in steps. And so what we talked about was that when it comes to radicals, the principal root, yes, we are going to learn how to take roots of complex numbers, find the roots of any complex number. We are going to learn how to find the principal roots of any complex number. But we don't want to be at the moment in all of algebra and even trigonometry, we don't want to be thinking about putting complex numbers inside of a radical at the moment. Yes, we'll be able to think about adding, subtracting, multiplying, dividing complex numbers, taking powers of complex numbers, but at least as far as principal roots and putting complex numbers inside of radicals, we don't want to do that at the moment. It's going to get confusing. The only little bit that we're going to allow ourselves to mix complex numbers with radicals is for this property here, which says that if you've got a principal square root, just the square root, and a negative number inside of it, a negative pure real number, that's it, then we can simplify this by taking out an I and leaving the positive principal square root. We can do that, but that's as far as we're going to go in all of algebra and trigonometry when it comes to radicals and complex numbers. Okay. In the fourth section, we increased the complexity of the equations a little bit. We went from learning how to solve linear equations in one variable to quadratic equations, which it's a polynomial equation, but now the highest degree term is 2, right? That's any quadratic equation in any number of variables. It's going to be a polynomial. Every term is going to be polynomial with the highest degree term being 2. Okay, but we focused on quadratic equations in one variable, and so what we looked at was 3 separate methods to solve quadratic equations. The first method is the more general method that we're going to use to solve any kind of polynomial equation, any kind, no matter what the degree is. And what we do for that method is we bring everything to one side. So for the case of a quadratic, we bring everything to one side, combine like terms, simplify. And when it's quadratic, we're going to have something like this, where just A can't be 0 or it wouldn't be quadratic, but B and C could be 0, whatever. And we're thinking about A, B, and C are real numbers, but they could be imaginary, and that would still be quadratic, but we're going to stick with real numbers. And we factor this. We factor this as much as we can, based on, we learn how to factor in pre-algebra. Then what we're left with is these product of factors are equal to 0. Then we use the zero product property to solve this, which just says that if any one of these factors are equal to 0, and these factors are going to be simpler than the quadratic, right? They're going to be like linear factors. If any one of these factors are equal to 0, then that's a solution. And so we can get all of the solutions by setting each of these equal to 0. Okay, that was the first method, and you can see how we could use this method to solve any kind of polynomial equation, as long as we can factor it. Okay, the second method was based on the use of the square root property, which says that if you ever want to think about taking the square root of both sides of an equation, so you would do that with the principal square root symbol. Well, what you're really asking is you're trying to figure out what are all of the, so if you had something squared, it could be x squared is equal to 4 or x minus 2 squared is equal to 9. You're really trying to ask the more overarching question, what are all of the numbers that when I square them that I get 4? You're not really looking for a principal root. You're using the principal root as like symbolically, and if you do this, right? But it's really not about the principal root. You're trying to figure out what are all the numbers that when you square it, you get 4. Here you're trying to figure out what are all the numbers that when you subtract 2 from them and square them, that you get 9. And we learned a principle, and this was just for, if you're doing this for the case of squaring, that you can do this with an equation. You can apply a principal square root to both sides of an equation, and that would be valid if you just put over the away from the variable term over the constant term, you put a plus or minus. Now you can still evaluate the principal square root of 9, the principal square root of 4. That's going to be positive, but with that plus or minus out front, you've accounted for that overarching question. Okay, and so with that, then, if you want to solve any general quadratic equation, you can use the process of completing the square combined with this square root property to solve it. Because when you complete this, you can take any quadratic like this and you can complete the square. And in general, what you're going to get is x plus some constant squared is equal to some other constant. And so you can apply the square root property and solve it. Okay, the third method that we used to solve quadratic equations was with the quadratic formula, which comes from, they took this general form of any quadratic. This is the most general form. You can take any quadratic and put it into this form, where a is not 0 because then it's not quadratic, and b and c can be any real number. And they applied the completing the square process on this variable form here to get the quadratic formula, to where you just take any quadratic, put it into this form with all the terms on one side and 0 on the other, and just plug the coefficients into this formula, and that's going to be the solutions. Okay, then we looked at applications of quadratic equations, word problems, which is really useful to get a sense for when these types of equations come up in real life situations. Okay, and then in the 6th section, we looked at 3 different types of equations. We looked at polynomial equations, absolute value equations, and radical equations. So polynomial equations was, the way you categorize a polynomial equation is that it's a polynomial equation that isn't linear or quadratic, because linear and quadratic equations are polynomial equations. So if the degree of some term is 3 or higher, then you're going to have you call it a polynomial equation. And you solve polynomial equations by using the zero product property. You bring everything to one side, factor it, set all the factors equal to 0 to get all the solutions. All right. Next was absolute value equations, which is any equation to where there's just one term that has a variable expression inside of the absolute value. If there's just one term, then we call that an absolute value equation. And we saw that the general method, we looked at the general method used to solve any kind of absolute value equation. We went beyond just the very simple cases that the textbook gives. And we saw that the process is that, so if you've got multiple absolute values, let's say, with anything, with anything inside of the absolute value, whatever, the idea is that we want to analyze all of the separate expressions inside of the absolute values and get all of the x values where that expression changes sign from positive to negative or negative to positive. Now, yeah, well, similar to inequalities, we're not dealing with complex numbers at the moment, because how do you think about the absolute value of a complex number? We'll have to learn that later. So with anything with absolute values or inequalities, we're not thinking about complex numbers. Okay, but again, you're looking for, you want to list out all of the different x values for every single absolute value in the entire equation, that expression, that it's a crossover from positive to negative, negative to positive, and then you plot those points on a number line. So you've got all these different points on a number line. Let's say this is 0, A, B, whatever. And you put these vertical lines, and now you're going to see all of these separate regions that we're going to need to analyze the equation. Because in these separate regions, we'll be able to say for sure that, okay, and for all x values within this region, this expression is going to be negative, or it's going to be positive or 0. And because of that, we can simplify the absolute value, because if x cubed plus 34 is always going to be negative, then we know we can say, okay, remove the absolute values, put a negative sign out front. Because it's always going to be negative, multiplied by -1, you get the positive. If it's going to be positive or 0, for sure, then you just remove the absolute value. And so in each of these regions, we'll be able to get a unique equation with no absolute values, and we can solve that equation and get these different values. Now, are those values that we get solutions? They are solutions only if we have to compare the value that we got to the region that the x value region that we're in to make sure that that value is in that region that we're analyzing. If it's not, then no, it's not a solution. If it is, then it is a solution. And we do this for each separate region as well as the boundary points. Make sure we account for every point, and that's it. That's how you solve any kind of absolute value equation of any kind of complexity. Okay, now a radical equation is any equation that contains a rational exponent or a radical. At least one term contains a rational exponent or a radical. And yeah, but now you might say, well, wait a minute. How do we classify? We have these absolute value equations, but is it absolute value linear or radical or whatnot? All of the separate so every time you go into a region and you have this equation where there's no absolute values that you're solving, whatever type of equation that is, then that's the type of absolute value equation you're dealing with. So if it's every time you remove the absolute values and you're solving an equation, if it's a radical equation, then that is a radical absolute value equation. If every time you're solving a linear equation, then it's a linear absolute value equation. Okay. So, but if at least one of the terms contains a rational exponent as a variable with a rational exponent, or a radical with a variable inside of it. So no, just because you have, 4 to the 3/4 in an equation, well, this is just a constant. It needs to have a variable raised to a rational exponent, or a variable with a inside of a radical. Then you have a radical equation. And we saw that we solve radical equations by isolating if there's multiple radical expressions, that's fine, but you start by isolating a single radical expression on one side with everything else on the other side. Then you raise both sides to the index of that radical, and that's going to remove the radical, because if you had like x to the 1/3, if you cube that, you get x. You remove the radical, right? Even if you had x to the 2/3. If you raise it to the index, you're left with x squared. The radical's still gone. Okay, and then from there, you remove one of the radicals, and then if there's still more radicals, you keep doing that same process. Then you isolate the other radicals. You raise both sides to the index of the radical until you remove all the radicals. Then you solve whatever's left. Now, if there's ever a point where you raise both sides to an even index, then all that means is that there could be extraneous solutions. So once you get your final answers, you're going to need to check those answers, put them into the original equation. They could be extraneous. They could be extraneous because you're going to end up with a negative under an even root radicand, or they could be extraneous because they just don't check out, because it's the process of squaring both sides. If you have x is equal to -2, now if I squared both sides, okay, x squared is equal to 4. Well, now I've lost the -2. If I try and go in the other direction, there's an issue, right? I guess plus or minus. You see, you've lost information. When you square both sides, it's irreversible. Okay, now the last section was about inequalities. So you've got two expressions on either side of one of the 4 different types of inequalities. And so we started with, we looked at linear inequalities in one variable. However, when it comes to inequalities, it's much easier to just look at what the general procedure is going to be to solve any kind of inequality, no matter what it is, no matter how complicated it is. The general procedure is always going to be, so you've got, let's just think about an inequality in one variable. So an expression of x on one side, one of the inequality symbols, whatever it is, and then an expression of x on the other side, no matter how complicated. What you're going to do is you're going to bring everything to one side. So you're going to have some big expression of x, and then the other side is going to be 0. Okay? Now, you don't have the skills at the moment to do this for any kind of expression, no matter how complicated. But trust me that once you're done with calculus, you'll be able to look at any expression, no matter what it is, and without an issue, you'll be able to analyze. So you'll be able to draw a number line. Right now we're just thinking about real numbers, and you'll be able to without any problem identify all of the different regions along the number line where this expression is positive, negative, or equal to 0. And you'll be able to map all of that out, no problem. You'll take any x expression, no matter what this is, and map out all of the regions where it's positive, the x regions, right, here, whatever, where this expression is positive, negative, or 0. Well, once you have that, then you've got the solutions. It's just a matter of writing out what the different intervals are. Because wherever this expression is equal to 0, that's not going to be a solution because this doesn't say equal. It's just wherever it's greater than 0, that's the solutions. That's the process. Now, however, you still, that sounds simple, right? Once you know how to find any where any expression is positive, negative, or 0, it sounds like, okay, well, that's all I need to know. You don't have everything you need yet. You need to understand the properties of inequalities. It's similar to the properties of equalities in that, adding things to both sides, subtracting things to both sides doesn't change the inequality. Okay, but there's one subtle difference. So when it comes to inequalities, if you have any kind of expression on one side and any kind of expression on the other side, and this could be any of the inequality symbols, you can add or subtract whatever you want to both sides and it doesn't change the inequality. You can multiply or divide both sides by any positive number that you want, and it doesn't change the inequality. You can't multiply both sides by 0, same thing. You obviously can't divide by 0. If it's a positive number, it doesn't change the inequality. However, if you multiply or divide both sides of an inequality by a negative number, then all you have to do is just flip the inequality. That's it. That's simple. That's it. And it doesn't matter if this is greater than, equal to, whatever, doesn't matter. Now you have all of the tools you need to solve any inequality. As long as you can once you can look at any x expression, no matter what it is, and find all of its positive and negative intervals and where it's equal to 0, you can solve any inequality, no problem. And I guarantee you, when you're done with calculus, you'll be able to do that easily. But you will need to, you might need to, whenever you start with the inequality, you might want to simplify it and subtract things from both sides, manipulate it to put it in different forms. You need to know how to manipulate it. You need to know that when you add, subtract things to both sides, it doesn't change anything. You can't forget that if you multiply both sides by a negative number, you need to flip the inequality or you'll make a mistake. But other than that, that's it. Okay, now, but a linear inequality is a special case where you can act, is really the only case. I would say in general, it's the only case where you can actually solve it like you do an equation, in the sense that if we have 3x plus 5, let's do minus 3x plus 5 is less than 17. Well, we can actually solve this in the same way that we would solve a regular equation. So subtract 5 from both sides. 17 minus 5 is 12. Divide both sides by -3. Flip the inequality. There's the solution. But in general, you can't really do this with any kind of equation. Like if you have a quadratic, you don't want to be squaring both sides of an inequality. That's going to get confusing. In general, it's just bring everything to one side, find where that expression is positive, negative, or equal to 0, and write out the solutions. That's it. Okay, now, compound inequalities. What is a compound inequality? This is similar to it's similar, but not the same as solving solving multiple equations, a system of equations. When you have a system, when you're trying to solve a system of equations, you've got these multiple equations. Let's assume this is all one variable, and you're trying to find any of the x values. Let's assume it's just real numbers. Any x value that when I plug it in here, it's a solution, but also when I plug it in here, it's a solution, and also when I plug it in here, it's a solution. Then that's a solution to this system of equations. If it's just a solution to these first two, but not the third, it's not a solution to the whole system. That's the idea. And that's similar to the idea of what compound inequalities are, but there is some differences because we're dealing with inequalities. One of the big differences is that with compound inequalities, it makes sense that we can have these and or statements between them that really don't come into play you can't really do that with multiple equations. You kind of could, I guess, but not really. And you do this, you have these ands and ors. The main reason is because when it comes to, if you think about it, when it comes to solutions of inequalities, in general, you can have these huge solution sets, right? Like x is greater than 4. That's like a typical solution to an inequality. Any value that's greater than 4 is a solution. You don't really get that with equations most of the time. You don't really have that with equations. In general, it's usually just like, okay, there might be 2 or 3 answers, or just one answer a lot of the time, one solution. Okay, so what a compound inequality is, we only really practice problems with compound inequalities involving 2 separate inequalities, but you can do this with any number of inequalities. You can have a compound inequality involving 5 inequalities, whatever. All you're doing is you're saying that, so you could have an inequality here, and that's combined with an and with this inequality over here. All you're doing there is you're saying, okay, this needs to be satisfied, this inequality, and this needs to be satisfied, then it's a solution. Okay, so you have this in a box here. You could combine that with an or on this inequality. So to satisfy this entire system, either both of these need to be satisfied at the same time. If that's not the case, but this is satisfied, then that's a solution. Or if it's not a solution to this, but it's a solution to both of these, then that's a solution. But like if it's just a solution to this and this, no, that's not a solution. And it makes sense that you'll be able to really do this kind of analysis with inequalities because, again, it's like when you've got a solution to this inequality would be x is greater than 4, any number greater than 4. Well, okay, there's a good chance that this might overlap with this. If this was less than 20, that's the solutions. Well, look, you've got these huge ranges here, right? So, okay, what overlaps with when x is greater than 4? What overlaps with anything x is less than 20? Well, that's anything greater than 4 and less than 20, right? So you're just going to be comparing these solutions to see whether they overlap, or if it's not overlap, it's either or. Like, in other words, if you had an and criteria, if x is greater than 4 and you had this as x is less than -2, well, there is no solution in this case to this and criteria. There's no overlap. But if you put an or here instead, well, then it's either one of these. You plug, it's anything less than -2 or anything greater than 4. Okay, we then looked at absolute value inequalities, which is any inequality where there's at least one term with an absolute value and a variable expression inside of it. And what we saw was that the mechanics for solving absolute value inequalities is exactly the same as absolute value equations. Exactly the same. It's the same thing in every way. The only difference is going to be that you're dealing with an inequality, not an equation. So you're gonna plot all your boundary points and see the different regions. Then you're gonna come to this region and you'll be able to remove the absolute values and you're gonna solve the resulting inequality. And then you're going to compare the result of that inequality. Let's say you got x is greater than 4, but here your x is less than 6. Well, you're looking for the and, the final solution is the and between these two. That's all the solutions for this region, right? Because it has to overlap with the area you're analyzing. So you take the and between those two, that's the solutions for that region. You get all of the solutions for every single region. Then you combine all of those solutions with an OR, because any one of those are solutions, right? Again, I want to make sure this is clear. So you have all the different absolute values in the entire inequality, right? You find where they cross over zero, and you plot those points, and you mark off these vertical boundaries. So we need to analyze all of these regions separately, just like we did with absolute value equations. So you come to like this region here first. Let's say this is x is less than 5. Well, with that, you're able to remove the absolute values, because that's the whole idea. And you're left with some inequality with no absolute values that we know how to solve. Let's say you solve that inequality and you get x is less than 12, less than or equal to 12. Okay, well, is this a solution to the original inequality? Well, no, because it just like with absolute value equations, it needs to match up with the interval we're looking at. So how do you tell if they match up? Well, you're looking at where they overlap. If this is saying that any value less than or equal to 12 is a solution to the simplified inequality that we solved, well then okay, yeah. So that means that all values that are less than 5 are going to be solutions. So we just write that. What we're doing is we're taking the and compound inequality between those two. So x is less than 5 are solutions to this original inequality. You do this for all of the regions, and you're going to get these different solutions. X is greater than 2, these different solutions. X is, whatever. And then you're going to apply an OR between all of these, because any of those are solutions. You're going to apply an OR between all of these, and you can condense it down to this final simplified form of here are all the solutions. Okay, so that's an overview of what we learned in chapter 1.